Hi everyone. We start chapter 5, 1 and 2 sample tests. We have several topics in this chapter. So one is the test about population mean mu. So for example, we test if population mean is equal to 100 for some data. And the second topic is to compare two population means. For example, the average height of male student is higher than average height of female students. So that kind of hypothesis. And the third one is to compare variances. So whether the first sample has larger variance than the other sample. So this is especially useful when we compare the accuracy of two models. So these are the main topics of this chapter. So we discuss the key concepts for testing also. Okay, so introduction. So recall that the hypothesis testing is a decision-making rule between the null hypothesis and alternative hypothesis. So in estimation, for example, to estimate population mean, our answer is numeric, but in hypothesis testing, we only have two conclusions, either H0 and H1. And the one thing we have to mention is that usually the two hypotheses are not symmetric. So H0 is rejected only when there is a strong evidence that H0 is unlikely. So H0 is accepted otherwise. So usually the situation is we want to claim the H1. And to strongly claim H1, that we should say that H0 is rejected. It's very unlikely. So that is our scheme. So that's why H0 is called null hypothesis. So basically we have no useful information. So null hypothesis, we say. An example. So suppose that we found that 51 out of 100 newborn babies are male. And we want to test if 50% of babies are male in the United States against not 50% of babies are male in the United States. So suppose these data come from the United States also. So, okay, so 51 out of 100 is not 50%. So sample proportion is 51 over 100. So actually 51%. But if you are we should reject H0? Probably not, because we only have 100 observations and 51 is very close to 50. So maybe just by chance we got 51 male babies, but in fact, possibly the proportion of male babies in the United States in the long run is 50%. So in this case, probably we do not reject H0. So that means we are kind of accepting H0. We don't say we accept H0, but we don't reject H0. So, but that means we still neither support H0 nor H1. So do you know are there more male babies or female babies? Actually, we have more male babies. Probably, genetically male is, the weaker than female. So 51%, probably a little less than 51%, but actually the proportion is not 50% in the entire population. Okay, so now that we study one sample t-test. So this is to see if population mean or sometimes population proportion is equal to specific value. In the previous example, p is equal to 0.5, but we will have more numeric example on population mean. So suppose that the following figures are starting salary for 7 math PhDs. 45,000 and 80,000, 50,000, 95,000, 65,000 and 110,000 and 48,000. So this is a kind of typical data from math PhDs. Maybe some people got a job in finance, then they may get these days even higher than this. But if you do postdoc, probably the salary is like the 45 to 50. That's possible. Okay, so we want to test if the population mean of math PhD salary based on all math PhDs in the United States is equal to 79,500 or not 79,500. Actually, 79,500 is the average salary, so population mean salary for all PhDs in the United States. So basically, we want to see if math PhDs have the same level of salary with other majors or not. We want to test that hypothesis. So then, what's the most useful information? So most useful information is whether sample mean X bar is far away from 79,500. If X bar is 100,000, probably that's significantly more than mu, so we can reject H naught. But if X bar is only 79,600, probably difference is negligible. So one important quantity is this X bar minus 79,500. But actually, we have one more important information. So sample mean minus 79,500. In addition to this information, the variability of the data is important. Okay, so even if, for example, the average sample mean salary of math PhDs is very close to 79,500, if data is like 79,600 and 79,700 and 79,650 and 79,550 and so on. Even though these salary are very close, you can see that these numbers are all larger than 79,500. So if you observe this kind of data, you can, confidently, if we have maybe the 100 data points like this, then we can confidently say that math PhD's salary is significantly higher than average PhD salary, but only slightly higher. So variability of the data matters. So it has to be considered, accounted for to see if we should reject H naught. So this is the important statistic. So just the deviation between sample mean and the hypothesis divided by standard deviation. Actually, S over square root of n is standard error of X bar. So numerator is the deviation from the hypothesis and denominator is the standard error. So this is in engineering called the signal to noise ratio. So this is a kind of signal size, but the denominator is the noise size. If signal is much larger than the noise, then we see something significant. Something is significant. And actually this statistic follows, this statistic T follows T distribution with degrees of freedom n-1. So you can see if this capital T is extreme or not based on this statistic. So, to be exact, if the X follows X, if the null hypothesis, the expectation of X is equal to mu naught, if this null hypothesis is true, so that means that this follows this normal distribution, then this T follows, capital T follows this T distribution with df n minus 1. So if the capital T is really extreme value of T distribution of with df n minus 1, then we can say that H naught is unlikely, because if H naught is true, this capital T should fall in a typical range of T distribution with df n minus 1. And this capital T is called T statistic. Why we say T? Actually, the original paper was published by our person whose anonymous name is student T. So that's why this is called T statistic, and sometimes the student T statistic. Yeah, so the idea is that, okay, so suppose that we have the density curve of T distribution of with degrees of freedom n minus 1. So this is density of T n minus 1. And if our statistic T falls in extreme range, so actually this range or this range, that is too extreme under this situation. So we reject null hypothesis. So if T falls in this range, T falls in this range, it's too extreme. So these are typical values, but these values are too extreme. So we reject null hypothesis. And if not, we don't reject. So this is reject H naught, and this is, so this center range don't reject H naught. So this is the rule. And this region, so this region is called rejection region. If you are interested in, you can make this figure with this code. So at first you plot density function. We have 7 observations. So T statistic follows T sub 6. So this is n minus 1. So T sub 6 distribution. So you can describe the density curve by this. Then we put these lines. So this, basically we put many vertical lines, actually the 50 vertical lines on each side. So this code describe that code. So this is the basic theory for one sample t-test.